Hi guys, myself Pranav is here to deliver today's presentation, Power Transformer Part 52. As the subject is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with to analyze the role of zigzag transformer. The effectiveness of using appropriate grounding transformer is of much importance since the power network reliability, short circuit fault current withstand capability to interact certain over voltage interference and to maintain basic insulation levels, etc., that would thereby to depend on the basic characteristics of neutral grounding system. A grounding transformer is typically designed with the philosophy one, to provide a relatively low impedance path to ground to either an ungrounded star or delta connected three-phase system. To make a provision of neutral point for grounding purpose of an ungrounded three-phase power system so as to pass ground fault current during line to ground faults. Number 3, to limit the magnitudes of transient over voltages which may have to occur during restriking arcs after current interruption in the breakers. However, ungrounded system that would have become grounded as soon as 3 voltage transformers or potential transformers, that is PTs, are being connected with the system as fault detector. Therefore, all the high voltage ungrounded system is thereby grounded through the high impedance of these PTs. As of the grounding transformer configuration, using conventional star delta transformer is usually not being cost effective as compared to the zigzag connecting transformer. So far the design is concerned, the zigzag connection as of figures 169 and 170 would have become much more conducive as because each of its winding has less than the line to ground voltage by a factor of √3. Hence, less power rating is thus to be required as compared to star delta transformer because it requires full voltage across all windings. Design power rating of zigzag transformer is thus to be concluded, that is power P equals to V line to ground to I neutral divided by √3. See the diagram, zigzag grounding transformer with the flow of fault current. Phasor voltage diagram in zigzag grounding transformer. During a single line to ground fault, the magnetic flux in the zigzag transformer coils are not equal in the faulted phase. Therefore, a zero sequence current flows through all the windings of the transformer, and at the neutral, they are added up. Again, I repeat, during a single line to ground fault, the magnetic flux in the zigzag transformer coils are not equal in the faulted phase. Therefore, a zero sequence current flows through all the windings of the transformer, and at the neutral, they are added up. The zigzag grounding transformer must have to be designed to act perfectly with the maximum fault current as well as a continuous unbalanced load condition supposed to be on the circuit. The neutral formed by the zigzag connection is undoubtedly very stable for an ungrounded three-phase system. Harmonic voltages, if imposed in the system, can be suppressed to some extent through zigzag windings due to have the opposite connection of winding coils. Zigzag units, once installed adjacent to load side, then the zigzag connection in power systems can trap triple harmonic, that is third, ninth, 15th, etc. Currents are produced by the nonlinear loads. The zigzag windings not only trap the harmonic currents, but also prevent them from traveling to upstream, where they may have to produce undesirable effects. Most important, the zigzag windings not only trap the harmonic currents, but also prevent them from traveling to upstream, where they may have to produce some undesirable effects. Salient points to be noted. A, as there would have been no galvanic isolation in between the transmission lines and the zigzag transformer windings, so that makes the transformer to act as a high impedance reactor. Again, I repeat, as there would have been no galvanic isolation in between the transmission lines and the zigzag transformer windings, so that makes the transformer to act as a high impedance reactor. B, under normal system operation, there may have a small flow of current only due to presence of certain leakage fluxes. Number C, because of its winding configuration, the positive and negative sequence current components are always being blocked. D, depending on the construction of the core as well as the winding connections, the zigzag transformer has offered a zero sequence impedance to the flow of zero sequence current. Hence, the zigzag connection that basically would have to impose a high magnetizing impedance to the flow of balanced positive and negative sequence currents, and simultaneously provides a much lower leakage impedance to the flow of triple harmonics and zero sequence currents. Again, I repeat, hence, the zigzag connection that basically would have to impose a high magnetizing impedance to the flow of balanced positive and negative sequence currents, and simultaneously provides a much lower leakage impedance to the flow of triple harmonics and zero sequence currents. If any occurrence of line to ground fault in an effectively grounded transmission lines, there must have to produce zero sequence currents only. G. Therefore, line to ground fault would not cause to flow the positive and negative sequence currents through the ground. As the zero sequence current only flows through the faulty line to ground, so the zero sequence voltage is equal to the line voltage. Most important. As the zero sequence current only flows through the faulty line to ground, so the zero sequence voltage is equal to the line voltage. This technical perspective has ultimately benefited the system by limiting the voltage rise on the remaining unfaulty phases, resulting no impact on the basic system characteristics of voltage and insulation coordination. J. As corresponds to system protection philosophy, imposed grounding transformer that should have the low zero sequence impedance and low no load losses, that is hysteresis and eddy current losses. Again, I repeat, as corresponds to system protection philosophy, imposed grounding transformer that should have the low zero sequence impedance and low no load losses, that is hysteresis and eddy current losses. Zero sequence impedance that would have to depend on the flux density distribution and leakage flux for each winding of the zigzag connection. The grounding transformer using zigzag connection is the most accepted configuration, as because the geometry of the zigzag connection would have become much competent to restrict the circulation of third harmonics. Each leg of a grounding transformer carries 1/3 of the neutral current and has line to neutral voltage. The main benefit of the zigzag connection is that the currents in the two hubs of the windings on each leg of the transformer flow in opposite directions, figure 171. Thus, if there is any DC component, then it is to be automatically cancelled. However, a zigzag transformer is generally more expensive to construct as a grounding transformer for a system because it is specifically designed exclusively for the system as per its own requirement. See the diagram. Zero sequence current flow in zigzag grounding transformer. Inserted impedance in neutral circuit. Transformer in parallel connections. In three-phase power generation, it is rather very common to have a parallel operation of three-phase transformers. Instead of using a single large unit, it is sometimes economical as well as much more convenient to install two or more transformer units in parallel. Single large transformer unit, if installed for supplying the entire load, then there will be an obvious possibility of total interruption of power during any breakdown of the transformer. But in case of using multiple transformer units in parallel and a fault occurs in any one of the transformer unit, then the particular faulty transformer may have to be taken out of service while the remaining transformers will feed the power supply. So, transformers operating in parallel would obviously enhance the reliability of supply system. However, in case of parallel operation, the most pertinent point is that the plant management would have the opportunity to frame out best possible comprehensive schedule programming for breakdown maintenance work. Therefore, for supplying a load which would have been excess of the rating of an existing transformer, then two or more transformers may have to connect in parallel with the existing transformer. Transformers are thus made to be paralleled to have the power systems more reliable, provide better power quality, prevent voltage sags, or for additional load requirements. But there must have some limiting conditions of connecting transformers in parallel so as to comply the best possible requirements for sharing of load patterns. In order to meet the increasing load demand, major findings that have brought the issue of parallel connection of transformers as a strategic solutions. 1. Single large transformer is always be vulnerable as well as uneconomical for handling large loads. Number 2, parallel connection of transformers is in many ways economical and of reasonable solution. Number 3, while the load demand increases over time and the existing transformer is not enough to meet that demand, then instead of replacing the existing one, another transformer is connected in parallel. Number 4, parallel operation that has to optimize the space capacity of the station also. Number 5, system availability, reliability, and operational flexibility would have been enhanced. This sort of application may have to maximize the system efficiency as because power transformers generally deliver maximum efficiency at full load operation. Number 7, comprehensive scheduled programming for spares and breakdown maintenance work can be achieved. Comprehensive schedule programming for spares and breakdown maintenance work can be achieved. Factual significance of using multiple transformer units in parallel. Number 1, have to facilitate strategic load sharing possibilities that ensure a balanced current distribution. Again, I repeat, have to facilitate strategic load sharing possibilities that ensure a balanced current distribution. Number two, establishing a redundant power supply system and minimizing the downtime. Number three, maximizing utilization efficiency of transformers. Number four, enhancing the system availability, reliability, and operational flexibility. Number five, comprehensive scheduled programming for spares and planned breakdown maintenance work can be achieved. Number six, it is rather economical to install number of lower rating transformers in parallel instead of installing a single higher rating power transformer. These six are the most significant purpose to use the multiple transformer units in parallel. Let's stop here, further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscription would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.